If you haven't heard of the term Doppler effect, maybe you have at least heard this. Well, that shift in frequency you hear is due to what's called the Doppler effect. So the Doppler effect is a shift in the frequency due to the velocity of the waves, how fast waves travel, how fast the thing making the waves travel, the source, and how fast the thing that is observing those waves is traveling. We are also going to look at the patterns that are formed when the velocity of the source, the thing making the waves, is traveling subsonic, slower than the speed of sound, sonic, traveling the speed of sound, or supersonic, traveling faster than the speed of sound. But the Doppler effect relates not just to sound waves, it will work with water waves or light waves. Any kind of wave would experience the Doppler effect. One thing I want to clear up right away is that the Doppler effect is not a shift in the loudness or the volume. Yes, it's true, as a race car gets closer to you, it's going to sound louder, and as it's further away from you, it's going to be not as loud, but that's not the Doppler effect. The Doppler effect is a shift in the frequency or pitch. It's going to have a higher frequency as it is coming toward you and a lower frequency as it is moving away from you. Frequency is measured in hertz, or how many waves pass by per second. So I'd like to develop an equation for you that will predict what the frequency that you hear is in comparison to the frequency that's being emitted by the source. In the previous example, it was a race car. So let's say that this is creating waves at a certain frequency, and those waves are spreading out like this. Now, maybe I should say before I continue that this animation uses very unrealistic numbers. For example, I'm saying these waves are spreading out at 10 meters per second, but the speed of sound is around 342 meters per second at nice warm temperature air. And then I'm going to say we're going to hear a frequency of 5 hertz, but we couldn't hear 5 hertz. It's too low of a frequency. 20 hertz is the lowest frequency that our ears can hear. And to put that in context, middle C on the piano is 256 hertz. Okay, so if I tried to draw this with realistic numbers, we would just get way too many waves and circles, and it would just be happening too fast. So let me explain with this animation here. The animation is going to run for, and we're going to slow down the animation, but it's going to represent 1 second of time overall. And each one of these little squares is going to be 1 meter. So that wave went here to here, which was 10 meters in 1 second. We can see that the wavelength is 2 meters, but also if it goes from here to here in 10 seconds, and that was 10 meters, it's only going to take 1/10 of a second to go each little square here. So as that source was emitting its waves, 5 whole waves passed by the observer in 1 second's time, so the observer heard 5 hertz. Okay, but now let's look and see what would happen if the observer were moving away from the source. This would be like a race car just sitting there revving its engine, but the person is running away real quick, or in a car racing away real quick. What would the sound of that stationary source sound like to our observer? So in this one, we're going to still keep the waves going at 10 meters per second. The observer is going to be moving away at 4 meters per second, and the source is going to be stationary. So as the waves are moving to the right here, so was the observer. Previously, 5 waves passed by that observer, but this time only 3 waves did. These 2 waves did not pass that observer in the 1 second's time because the observer was moving away from it. The source was still creating 5 hertz, but this time the observer only heard 3 waves in a second. They only heard 3 hertz. And there is an equation, and we're going to develop this equation. We're going to kind of get a sense of how to use this equation. But this F here stands for frequency, but it is the frequency of the source. Just what is the source doing? How many waves per second is it creating? And we call this F prime. If you're in calculus, you might recognize that as the first derivative, but we are not using it in that sense at all. F prime here just stands for the new frequency. So this is the frequency that is being emitted by the source, and this is the frequency that we would hear as the observer. V is the velocity of the waves. So in this case, the waves were traveling 10 meters per second. Sound waves travel about 342 meters per second. Light waves travel at 300 million meters per second. So this is just how fast the waves themselves are traveling. This is the velocity of the observer, and this is the velocity of the source. And you can see sometimes we're going to add, sometimes we're going to subtract, sometimes we're going to subtract, sometimes we're going to add. So we have to be careful with which is which here. So in this example, the source was stationary, so its velocity was just 0. So 10 plus or minus 0, it's still just 10. To decide whether we're going to add or subtract, we have to remember that as a race car is coming toward you, you hear a higher frequency, and as it goes away from you, you hear a lower frequency. Okay, so it goes from higher to lower as it approaches and then goes away. Now, just like with any fraction here, if the numerator is getting bigger, then that would also be getting bigger. Okay, and if the numerator was getting smaller, well, that would also get smaller. The fraction was getting smaller overall. Okay, so we knew that the observer was moving away. We knew that we would get a lower frequency. So we knew this number here had to be getting smaller. We were subtracting the velocity of the observer to get a smaller number in the numerator. Makes a smaller number overall, and that would give us a smaller frequency. And when we take that, we get 6 divided by 10, which is the same thing as 3 divided by 5, and then times 5, we get the same frequency as what we thought we would. All right, let's do this again, but this time we're going to have the observer moving toward the source at the same velocity as it was previously. Now this little purple line here starts 2 full waves in front of that blue line. So when I start the animation, we got 1, 2, 3, 4, 5, 6, 7 waves passed in that 1 second of time. So 7 full waves passed in 1 second. 5 waves was the frequency of the source, but the observer is going to hear 7 waves because they passed by 7 waves because they were racing toward it and they heard a higher frequency. So this time I'm going to add 4 to there. We knew that we should have a higher frequency, a larger number of waves, so the numerator of that fraction must have been getting bigger. And 14 divided by 10 is the same thing as 7 divided by 5 times 5 is the same frequency that we just measured there. All right. Now, this animation here is the same one I've just shown you, where the source is stationary, and we just get a bunch of concentric circles. All the circles have the same center. But now I'm going to have the source moving. So when the source was right here, it created a wave that's going to start to spread outward. But the next time it creates a wave, that source is not in the same spot. It will have moved over here to the right a little bit. So the next circle won't have the same center as the outer circle. And watch what happens to both of these. We'll pay attention to down here. Every time that emits a wave, that wave has the center where it was when the source was there. And you can see all these circles are no longer concentric. That the source moved from here to there in the same amount of time the wave moved from here all the way to over here. It looks like the source is moving a little less than half the speed of sound. And then here, the source was stationary. It wasn't moving at all. Okay, so let's do that same thing. We're going to zoom in on it a little bit. This time I'm going to keep both observers stationary, and the velocity of the source is going to be about half the velocity of the waves. So there it goes. This person isn't hearing anything until right now. Okay, so the first 0.8 seconds, that observer wasn't hearing anything. They only heard 2 waves in the last 0.2 seconds. Remember, one of these waves travels each square in 1/10 of a second. So this observer heard 2 waves in 2/10 of a second. That's the equivalent of 10 hertz. If they had heard it for 1 whole second, then they would have had 10 waves. All right, so let's see how that equation works over for this one as well. This person was moving away, and they only heard 3 waves in 0.9 seconds, so they heard 3.3 hertz. And same thing as before, but this time the observer was stationary, so its velocity was 0. And now I have to decide, do I add or do I subtract? Well, it's the same idea. If the source is moving away from you, you're going to hear a lower frequency. And if it's moving toward you, you're going to hear a higher frequency. Okay, except this time, the velocity of the source is in the denominator down here. So if the denominator got bigger, well, the whole fraction would get smaller, and we would hear a lower frequency. So we're going to add the velocity of the source so that the denominator gets bigger. So what we have is 10 divided by 15 is the same thing as 2 divided by 3. But when 10 divided by 15 is 2/3. I can do math. And 2/3 of 5 is 3.3 hertz. Back to over here, the observer was moving away, so you should hear a lower frequency. And if the denominator here got smaller, the whole fraction would get bigger. So that's why I chose to subtract, so that the denominator got smaller and the whole fraction got bigger. But now I have 10 divided by 5 multiplied by 5 is our 10 hertz. Okay, and then we can just do that again here real quick, but this time with a little bit higher velocity of the source. Previously we kind of paid attention to how the waves are passing here, but let's pay attention to how the waves are passing this guy this time. See, we get 2, 3, not quite. Wait, we had 3 full waves. I did do that wrong. 3 full waves pass by that guy in 1 second. Okay, so they're going to hear 3 hertz. They had 3 waves passing by in 2 seconds, or 0.2 seconds. Remember, the wave passes there. It takes 2 seconds, or 0.2 seconds to go those 2 distances there. So 3 divided by 0.2 is 15 hertz. 3 divided by 1 is 3 hertz. And again, I'm adding here because the denominator needs to be getting bigger so that we get a smaller frequency. And we get the same as what we did there. I am subtracting here because the denominator needs to be getting smaller so that we get a higher frequency, a bigger frequency. Okay, so we're just deciding whether we add and subtract, or add, depending on whether it's coming toward you, you should get a higher frequency, or moving away from you, you should get a lower frequency. And we get the same answer as we did there. In this example is just putting those two things together. The source is moving toward the observer, and the observer is moving toward the source. Okay, so having the source move to the right is going to really make a high frequency there, a short wavelength, but moving toward it is going to make a really much higher frequency. And the same thing here, it was moving away, so you should hear a lower frequency, and he was also moving away, so you hear a really low frequency. The numerator should be getting smaller, the denominator should be getting bigger, and the result makes a much, much smaller frequency. Here, we knew they were going to have a really high frequency, so the numerator was getting bigger because we added, and the denominator was getting smaller because we subtracted. If we keep that same picture where the source is moving to the right, but now the observer is also moving to the right, well, it's going to be the source was still positive on this side and negative on this side, but this time it was moving toward the source, so the numerator is going to be getting bigger, and it was moving away from the source, so the numerator should be getting smaller. We could memorize these conventions, that positive velocity of the observer if it is moving toward the source, or negative if it's moving away from the source, negative velocity of the source if it's moving toward the observer, or positive if it's moving away from the observer. You're going to forget that, but if you just think of numerator getting bigger, this gets bigger. If the denominator gets bigger, this gets smaller. Okay. And I'm wondering how many of you have ever been the victim of this equation? Well, maybe victim is the wrong word. Maybe just the application of justice. Meaning you were caught in a speed trap, you were speeding, but what happens here is the radar gun here is sending out light, and light travels at 186,000 miles per second, 300 million meters per second. But the device here knows how fast the observer is traveling. In this case, they were stopped. But when those waves bounce off your car and come back, they're going to come back at a different frequency. So knowing how fast light travels and how fast the police officer was traveling, and knowing the frequency of the waves that were being emitted here, measuring the frequency of the waves that return, you calculate the velocity of the thing moving. And I did say that wrong. It would be this is the velocity of the source. No, I did say that. It is the velocity of the car, the source. Had to think about that for a second. Doppler radar, you may have heard that, but it just sends waves out, and when they hit the clouds, some of those waves come back, and that will allow you to, by measuring the frequency that you sent out and the frequency that returned, you can figure out how fast those clouds are moving. And then depending also on the density of the clouds, like how much water is in them and how much activity, the waves come back a little different as well. Okay, so let's do a little bit more examples with light. Okay, we have the visible spectrum here: red, orange, yellow, green, cyan, blue, and maybe a little bit of violet here. Frequencies higher than violet are ultraviolet. Frequencies lower than red are infrared. But red are low frequencies, and then we get progressively higher and higher frequencies. One interesting thing about any element, we'll look at hydrogen in particular, is that if you had a container of hydrogen gas and you sent all the colors of visible light through it, hydrogen is going to absorb very specific frequencies of light. So that frequency got absorbed, so did this, so did that, so did that, so did that, and so did that. And if you do the opposite of that, if you take a hydrogen gas and send electricity through it so that it gets so excited, those hydrogen atoms begin to give off light. They will give off the exact same frequencies of light that hydrogen absorbed when you passed light through it. It has to do with quantum physics and the fact that when electrons orbit the nucleus of the atom, they orbit as a standing wave. We know a lot about that. And there's only certain standing waves that are allowed. And as the electron jumps in and out, it's going to absorb energy or give off energy of very specific frequencies. We studied more about that in second semester college physics or AP Physics 2. But with that in mind, we would often call these neon lights. Well, there's very few neon lights there because neon is a gas. Sodium is a gas, and when you send electricity through it, it will glow yellow. So these yellow ones probably have sodium in it. If they are blue, like the pants here, they probably have mercury in it. But if they're pink, then we can probably call those neon lights, because neon gas gives off frequencies that mix together to give you pink. So as we look at galaxies way out there in deep space, this was taken by the Hubble Space Telescope, these galaxies are not just sitting there, they are moving. And we know how fast light moves, but if we were to look at the light and very carefully analyze what frequencies of light are being given off, if we see this pattern, we say, I recognize that pattern as hydrogen. But if those galaxies which have hydrogen in them are moving away from us, the frequency of light that comes toward us is going to be shifted. The reds are going to shift to infrared, the yellows are going to get shifted to orange, the greens are going to get shifted to yellow, the violets are going to get shifted to blue. Everything's shifted toward the red. And if we measure the shift in frequency, what the frequency we know it should be versus the frequency we received, we can calculate how fast that galaxy is moving away from us. If the galaxy was moving toward us, then they would be shifted toward the higher frequencies. We call it blue shift. The reds would shift to the oranges, the violets would shift to the ultraviolets, and again, we could measure how fast that object was moving away from us. Edwin Hubble did a huge survey of many galaxies and found that on average, the majority of the galaxies are moving away from us. One other thing he discovered was that the galaxies that are farther away from us are moving away from us faster. So if like these are all different galaxies, the farther galaxies were moving away from us faster, they would have had a lot bigger redshift. Galaxies that are closer were not moving away as fast. All the galaxies are moving away from all the other galaxies on average. And that was the first evidence for the universe expanding. All right, so now we've looked at things going subsonic. Let's look at what happens when something's going sonic. So this is subsonic, but this is going sonic, where meaning the object is traveling the same speed as the waves it is making. And notice that as the waves get further and further out here, the object is just staying with exactly as fast as those waves are traveling. If these are sound waves, well, that's compressions and rarefactions of air. And if all in right where that object is, right immediately in front of it, as it's trying to push through that air, it's compressing that air. Normally that compression could get away from you, get out in front of the object, but we're traveling the same speed those waves travel. So you're just going to get a stronger and stronger and stronger and stronger compression, and it's going to be like super dense air. Another name for going sonic is going Mach 1, and it's named after Ernst Mach, who photographed a bullet going faster than the speed of sound. I'll show you a picture of that in a second. It was thought for a long time that it would be impossible to go faster than the speed of sound because the air in front of you would get so dense it would prevent you from pushing through that. But Chuck Yeager on October 14, 1947 in the Bell X-1 was the first person to travel faster than the speed of sound. One interesting fact is that the Wright brothers on December 7, 1903, first people to fly. 1903 to 1947 is 44 years. So we went from not being able to fly to being able to fly faster than the speed of sound in just 44 years. An incredible leap of technology. These little arrows on here, these little needles, are helped to slice through that super dense air that is in front of you. Okay, so these waves that are being created get super dense as you go the speed of sound, and you have to be able to slice through that. You do not hear a sonic boom for breaking through the sound barrier. That's a misconception. When this thing breaks through that, that's not when you hear a boom. Okay? If an object is going faster than the sound it is traveling, okay, it's already broken through the sound barrier, now it's going faster, you can see that the object is getting ahead of the waves it's making. And if I add a few more waves, well, actually in this picture here, it looks like the object traveled about twice the distance as the waves did in the same amount of time. This would be traveling about Mach 2. If I add a few more waves to this, it's a little easier to see that all along that edge right there, all those compressions are lining up. Okay, and right along there, you would get this super compressed air, which is what creates the sonic boom. So if you're out here and this plane is flying, you're not going to hear a sonic boom yet. It's only when that compression hits your ear, boom, that's when you hear a sonic boom. And if the object is traveling really fast, then that's how fast sound travels, and that's how fast the object was traveling. Okay, this is going to be a very narrow cone-shaped shock wave. And this object was traveling 3, maybe 4 times how fast sound was traveling. The SR-71, look at the shape of that plane. See how the wings are way far back like this, and there's really not a lot there? It's that the whole plane has to stay out of that shock wave. If the wings were to get into that shock wave, it could rip the wings apart. And Ernst Mach, like I said, was the first person to photograph the shock wave of an object that's going supersonic. Commercial airliners have been forbidden for traveling across land because of the shock wave, the sonic boom that would hurt. It would rattle windows, it could crack windows. It's very annoying for people on the ground. And this is the Bell X-59. They're just X-59 that is designed to go faster than the speed of sound but not produce a shock wave. And it's very uniquely designed to help cancel out the shock wave. And instead of hearing a sonic boom, you hear a sonic thump, which doesn't rattle windows, and you might not even notice it if you're not paying attention. Anyway, that's a little bit about the Doppler effect and the shift in frequency as waves come toward you versus away, and then what the waves look like as you're going subsonic, sonic, or supersonic. Hope you enjoyed.